Hello folks, in this video I'll be reviewing Newton's laws and applications and uniform circular motion, and this will be it for the review. Again, I'll be telling you the general ideas we talked about, types of questions we could have, and then we will be solving these type of questions next Monday and Wednesday. So Newton's laws and applications. We had three Newton's laws we talked about. First is the law of inertia. If an object is stationary, it wants to stay stationary forever. If an object is moving, it wants to move forever unless a force is acted on it. And the second law was the one that we used mostly in problems, is if we apply a force to an object, the object will be accelerating, and the acceleration of this object is directly proportional to the force and inversely proportional to the mass of the object, which gave us an equation. So we have an object with mass m, and with a force, let's say there is no friction, we learned about all these forces already, F will be equal to m times a in general. And then we moved on action-reaction, the Newton's third law, action-reaction, also called action-reaction law. If there's a force acting on an object, the object will be exerting the same, exactly same magnitude force in opposite direction to the object that is applying this force to. So if I hit this wall, it will be hitting me back. The same examples I am given, but that is generally is action-reaction. If there's an action force on some object, there will be a reaction force from the object that is equal to the action force in opposite direction. The first and third law are generally used as an idea. We found the normal force using the third law, Newton's third law, action-reaction. If there is a force acting on a surface perpendicularly, and there will be a reaction force, and this force was always normal. And normal force was called the force that is always perpendicular to the surface and is equal to the forces, normal forces applied to the surface. If we have more than one masses, for example, M1 and M2, and if we are pulling them with more than one forces, let me show you an interesting one. Maybe we have F1 pulling in the right direction, and we had F2 pulling in the opposite direction. For this one, we still use the Newton's second law, but now we have to more generalize it and use the total force in the system is equal to total masses in the system times the acceleration. So if we want to get to the acceleration, we need to find the total forces, which is a vectorial addition. We look at the direction of the forces and we add them up. At this point, we have to be careful to choose a positive direction and show the forces in that direction to be positive. Negative direction, show these forces to be negative in this case, and add the masses to find the acceleration. Excuse me. Another thing we said, force is a vector, acceleration is a vector, and force and acceleration are always in the same direction. Because of that, we will choose the direction of total force to be positive if we can know the direction of total force, or the direction of acceleration to be positive. This is again a matter of choice only, but if we choose this, we will make less mistakes in problems. So for this one, we don't know which force is larger, we don't know which way the total force will be. We just choose arbitrary directions. Let me choose positive direction to be that, and negative direction to be that. I don't know the direction of acceleration, it will be the same as a total force, so I'm just leaving that. And I'm going to write down this equation. I'm going to say total F is equal to the vectorial addition of F1 plus F2. Right? The same total force is also equal to total mass times A. That's what we generally do if we have a complicated system. First, we find the total force by vectorially adding all the forces applied to the system, and then equate this to total mass times A to find some values. And here, this is vectorial addition. As I am going down to magnitudes, I have to look at positive and negative directions. If I put this sign, that means they are vectorially added. But if I take this away, that means I'm looking at the magnitudes of the forces and take care of the plus and negative signs to do this arithmetic correctly. So F1 is positive, I'll take F1 as positive, F2 is negative in my choice, minus F2 is equal to M total is M1 plus M2 times A. Here we are slowly moving into the applications of Newton's laws actually. So this was the idea. Over here, for example, if I know these forces, masses, I can calculate A, or if I know A and forces, I can calculate masses, and so on. A lot of questions could come out of that. Now this would be a simple one. Here I automatically assume the zero friction. So frictional force is ignored in here. If there was frictional force, I also have to put this into account with which question I have to know the direction of motion, because frictional force was always opposite to the direction of motion. I am not going to reveal the forces of nature, which is a bit long, but I'm going to be quickly telling you the type of forces we were seeing. So frictional force we were seeing, first of all, normal force and tension force along the road. Here we will have tension force as well. And we had gravitational force we use in certain motion as well. So let's review these forces actually by solving some, or talking about some questions. I don't want to solve many and spend a lot of time, it should be very long. But let's look at an example. Let's say I have a mass staying here, and there is a kinetic frictional coefficient. Mu k is equal to 0.1. And there's a force pulling this. An object is going in this direction, so I know the acceleration. Let me not give you a value in here, it might not work. I didn't think through this. So let's say we had mu k only. It's mu k. And we are analyzing this motion. We are asked about frictional force, for example. We said we have a force, we have an acceleration. What is the frictional force? We know the mass, and the object is moving in this direction. If we know that the object is moving in this direction, acceleration is in this direction, we will say automatically this is the direction of motion and the direction of total force. So we say F total will be in this direction. And then using the Newton's second law, F total is equal to M total times A. We reach to some values. And here in the opposite direction of motion, we will have kinetic frictional force, Fk we called. And if we are solving for any type of frictional force, we had kinetic frictional force if an object is moving, and it was equal to mu k times the normal force. Normal force is sometimes called Fn, sometimes called N. I'll stick with Fn because N is computed with Newton units of the force. I want to stop and tell you that the unit of force is Newton, large N. Unit of acceleration is the same, meters per second squared. Unit of mass will be taken as kilogram for MKS units. So this will be frictional, kinetic frictional force. If the object is stationary, not moving, then it will have static frictional force. So kinetic friction, let's say. We'll call it Fs, and is equal to mu s times still Fn, still normal force. But the difference between static and kinetic frictional force is these constant. Kinetic frictional constant coefficient is slightly smaller than static frictional coefficient. To find N or Fn, normal force, we always look at the total forces applied to the surface. So here, the force pushing on the surface is only mg. So here N, upward force, will be the reaction from the surface, always perpendicular to the surface, always, and Fn here is equal to mg. Now if I want to solve for this question, this is the general equation I will be using. And I'll apply this, do similar steps like in here and solve it. Let me quickly show you that, and I'll move on after there. Mg is the weight of the object, by the way. Sometimes the mass is only given, we use G, gravitational acceleration to find the weight. Sometimes could be weight given as Newton, just then use the weight. So applying the Newton's second law there, we say total F is equal to M total times A, vectors. It is also equal to total forces here. This is our positive direction, so F, applied force, will be positive and frictional force will be negative. It will be equal to F, applied force, I'm jumping into magnitudes in here, minus frictional force. Again, if I think vectorially, this is vectorial addition of these forces. And if we are adding vectors, the direction matters. We choose positive directions, negative directions, and solve for the forces. And if we have M in here, we don't know A, let's say, this is equal to F minus F. Kinetic frictional force. For the kinetic frictional force, this will be our equation, mu K times Fn, and Fn is equal to mg. Let's put these in, we'll have Ma is equal to F minus mu K times Fn, enter that. And now we enter the value we find for Fn, normal force. We'll be end up having Ma is equal to F minus mu K times mg. This is not always the case. This is actually a question of Newton's applications. We said for the Newton's applications we had equilibrium and non-equilibrium. If we are in equilibrium, total forces are zero, acceleration is zero, there's no acceleration, or we have the object is either stationary or has a constant velocity. If acceleration is not zero, then we end up having these. If acceleration was zero, then we'll have zero in here, do the same step. So this would be a non-equilibrium question. Now, if I am to have another type of motion, let me see, then normal force will be different. We solved questions on the lectures about Newton's laws and applications. Normal force could be different, so we could have this type of an example. For example, let's say I have a mass. Now there's a force pulling it, but it has an angle horizontal. I'm not going to give a total example in here, but I'll just show you what Fn, normal force, would be, and what would be we would be looking at as the total force of the system. So this is F, it has an angle and horizontal, there's a friction. Let's say object is moving to the right, again with an acceleration. There will be a frictional force opposite to the motion, so we'll have Fk, the object is moving, and Fk is still equal to mu k times Fn, normal force. This all still holds. And the second law still holds. Total F of the system is equal to m total times A. It still holds. To find the total F of the system, we look at all the components of the forces along the x and along y. And we generally, by looking at the components, we set up our xy system that is appropriate for our question. This would be the xy system. And we take the direction of motion to be positive. Let me open my light again. Let's find the components of force F. It will have an x component along horizontal, Fx. It will have a y component along vertical. Fx is always equal to F cosine alpha. Again, alpha being the angle in between force and the horizontal. If you're using the vertical angle, it will be different. We didn't touch to that. If you're comfortable with it, you can use it, but other than that, I'm not going to be using it. And Fy will always be F sine alpha. Again, the angle with the horizontal. So we have Fx, Fy. Fx is pulling the object to the right. Fk, frictional force, is pulling backward. But the object is moving in this direction. Question gave it to us, and it has an acceleration. So this is again a non-equilibrium question. We have upward Fy, and we always have downward mg. Now, along horizontal we have a motion. Along vertical we do not have a motion. Along vertical forces are on equilibrium. We have mg pulling down, Fy pulling up, pushing up, or pulling up, it's okay. And we will have a normal force in the same direction as Fy. And again, along vertical, we have total Fy, which is 0. Along horizontal, we have total Fx, which is not equal to 0, is equal to m total times a, and there's a motion along horizontal. Using the equilibrium, this is an equilibrium case, and this is a non-equilibrium case. The whole system is not in equilibrium because we're moving along horizontal, but along y it's not moving, there is no acceleration, so it's in equilibrium. By using this fact, if the system is in equilibrium, total force is 0. Thus, we can directly jump to the fact that total forces pulling upward are equal to total forces pulling downward. Why? If I write down all the total forces and choose a direction as a positive, let's choose mg direction to be positive and upward direction to be negative, we will be, or let's choose general xy directions. Upward direction is positive, downward negative. Would make more sense in our xy coordinate system, but opposite is also perfectly fine. We'll be adding all these vectors vectorially to find total Fy. So we'll have Fn plus Fy. Let me call this actually total y because we already have Fy. This is not the same Fy there. F total y, total force, y component of total force. We can also call this F total. These are Fx involving this force only, but F total is involving all the forces in here. So we should clarify that actually. Sorry about that. This is F total, and this force is called F, have x and y components. So Fny, Fy plus mg vectorially though is equal to 0. If I go into magnitudes, now I have to look at plus minus directions and put the magnitudes in. Fn and Fy are positive, mg is negative. My equation will be F normal plus Fy. I draw up the vector sign. Now I'm looking at the magnitudes. Minus mg is equal to 0. If I am looking for normal force in here, it is not equal to mg anymore. If I solve for normal force, I will have normal force is equal to mg minus Fy. So, what happens when I go into the horizontal motion and write down my equation? I'm going to write down my Fk in there. Fk is equal to mu k times Fn. And enter an Fn from here. I will have Fk is equal to mu k times mg minus Fy. It is not mg anymore. This is a different system. After I get that from the horizontal direction, I go into, vertical direction, I go into horizontal part. I'm now writing down total Fx. Total Fx will be this direction to be positive, opposite direction negative, like an xy coordinate system. Motion is along this direction, so we say, let's jump into the magnitude part directly. That's what we did generally, but that's where it is coming from. So I'm not going to show the same in here. I'll directly jump into the magnitude part. Forces in positive direction, Fx, only, right? Minus forces in negative direction, Fk, is equal to m total times a. My m total is m only in here. There. And that's it, we're done. We found Fk value already in here. We're going to enter that. Fx is f cosine alpha, and we're going to reach our values. So let me put these as well. Enter Fx and enter Fk in here. We have f cosine alpha minus mu k times mg minus Fy, which will be f sine alpha, right? Let's write this better. Mg minus Fy is equal to m times a. From here we enter whatever values we know and so forth, whatever values are asked. So this would be one of two medium to complicated questions we could have about equilibrium. We have x components, we have y components. Find all the components vertical and horizontal. Look at the motion or equilibrium along vertical and horizontal, and solve for the questions. This would be a non-equilibrium question. There could be simpler equilibrium questions as well. And looking at the time, I don't want to make this as long as the other one actually ended up being quite long. Let's talk about an equilibrium question. An example, in equilibrium, again, the object could be moving with a constant velocity or stationary. In both cases, acceleration is 0. And using Newton's second law, and total times A, total force is 0. So let me draw. We solved a question. We solved question in the lecture videos. Watch those, or if you have your notes, review them. And we solved the question in the midterm review part. So generally we have equilibrium questions similar to that. Let's say a mass is hanging from here. They give us some angles. They could give us this angle, for example, alpha. This will be equal to this angle over here always. Give us some values. Let's say we have T1 that is given. Let me give you some values in here to see. We have T2. Let's say alpha is 30 degrees. T1 is 10 Newton. M is 2 kilogram. Yes. Let's say they also gave us this angle 60 degrees. And they are asking us what is T2. If the system is in equilibrium, first of all, we find all the components. mg is pulling us down. If we have 2 kilograms, it will be 2 kilogram times 9.8 meters per second squared. We find that. Go ahead and find these. I'm not going to solve it exactly. I'll show you what you have to do and leave it up to you to solve and find the values. We will have T1x to the right. Again, I'm setting my system, coordinate system, as this is x. Taking this to be plus, y taking upward direction to be plus. Directly a matter of choice again, but this works good in the equilibrium question. So we will have T1x is equal to T1 cosine 30 here. We know the angle is horizontal. We know T1y upward direction. If we know T1, we can find both. So T1y is equal to T1 times sine 30. For T2, use black maybe, I don't have many colors. T2x is equal to T2 times cosine 60, and we have also T2y. And this is equal to T2 times sine 60. Now we have all the forces. Upward we have T2y, T1y. Downward we have mg. System is in equilibrium. Total F is equal to 0 vectorially, which means total Fx is 0 and total Fy is 0. Let's jump in the magnitudes here and look at the direction to find the values. If we have a system in equilibrium like this, this fact gives us that the total forces pulling to the right are equal to total forces pulling to the left. Total forces pulling up are equal to total forces pulling down. So for Fx, total Fx is equal to 0 will give us total force pulling to the right is T1x is equal to total force pulling to the left, T2x, right? And that is it. This can actually give us the value of T2 directly. And total forces pulling up, we have T2y plus T1y pulling up, right? Two forces are equal to total forces pulling down, mg. And these are the equations we will be using to get to any values asked. Why then solve these actually if I didn't give you the mass? Let's say I didn't give you the mass. And I am asking you the value of mass and value of T2. We should be able to find both of these because we know T1, from T1, x is equal to T2x. We can reach T2, do that. And then using T2y, T1y, we can reach mg and find m from there. Perfectly doable. And that is it for Newton's laws and applications. For circular motion, let's move on to circular motion. Maybe I'll just give you 10 minutes reminders and then I'll have to finish this. review as well. Uniform circular motion. We have now angular values and linear values. We talked about the kinematics. We talked about the velocity, acceleration, the distance traveled in terms of linear values, always along a line, either along the x or horizontal, along a vertical line. Now we'll be talking about angular distances, angular velocities, and angular accelerations will come in the non-uniform circular motion as we learn, but it's not in this part yet. So we have a motion along the circle for uniform circular motion, and the circle will have a radius, of course. We have an acceleration along the circular path, what we call tangential acceleration. We call this V in the beginning, so we can call this V again. We have angular velocity, what we call omega. And we had time for one rotation as period. Time for one rotation. For one revolution. The unit is second. We had frequency revolution per unit time per second. We generally use revolution per second, let's say, and it's second to minus one, or also called hertz. We had these values. If we know the distance traveled along the circle is the linear distance or tangential distance, and we have angle spanned as angular distance. Let me take this R. So the angular velocity spans this angle in time, and the linear velocity or tangential velocity travels along the circle. And we said the tangential velocity is equal to 2 pi r over t. This will be on your formula page. R is in meters, t is in seconds, and we of course will be in meters per second. We said angular velocity is equal to 2 pi over t. Since t is equal to 1 over f, let me also tell this in here, or f is equal to 1 over t, vice versa, both are the same thing. Both are working if you switch these two values. So f is also equal to 1 over t, both works. Replacing t by f in here, 1 over f in here, we will have angular velocity is equal to 2 pi f. So if you know f, you can find angular velocity, or if you know t, you can find angular velocity. Same in here, replacing t by 1 over f. Tangential velocity is also equal to 2 pi r times f. Also take this in brackets, in a box. The unit for angular velocity is rad per second, t is per second, and rad comes from the fact that we have 2 pi in here. Now, if we look in here, we have omega is equal to 2 pi f, or 2 pi over t. So this involves omega 2 pi over t, right? Or 2 pi f is also in here, which means this results that we can also show tangential velocity as omega times r. We also have centripetal acceleration. It's defined as the acceleration causing the change of direction of this velocity. The value of velocity magnitude is constant, but the direction is changing is because we have a centripetal acceleration. And whenever we have an acceleration in direction, there will be a force, what we call centripetal force in here. And centripetal force is equal to m times a centripetal. Centripetal acceleration is equal to either v squared over r or omega squared times r. Entering this in here, we got centripetal force is equal to m omega squared r, or equals to m v squared over r. And I believe these are all the equations we have, and all these equations will be on your formula page. Let me also check that to make sure that I include them in your equations. In your formula page. Yes, looks good to me. Now, there are different applications of this motion. There could be a motion along the track, a car traveling like a roller coaster. We might be asked about finding the normal force, where we use actually Newton's equilibrium conditions or non-equilibrium conditions. So involving now one more force, which is centripetal force. We also said although the physically centripetal force is towards the center, the object feels it away from the center itself because of the inertia or reaction. The objects in here reacts to the force, it will push itself behind in the opposite direction. So it feels the force, centripetal force in the opposite direction. To solve the questions easily, we say we consider the centripetal force, which is felt by the objects, is always opposite direction, to be opposite to solve the questions easily. And in this case, if we have a rope, for example, we have a horizontal circular motion. We will only have, so let's say this is the surface I'm rotating, we will only have centripetal force, and I'm looking into the value of tension in the string. It will always be equal to centripetal force. Force pulling inwards towards center will be tension. Force pushing outward on the object, this is how the object feels the centripetal force, will be Fc, and T always will be Fc. At point A, let's say, point B, point C, all the same, or D. If this motion is a horizontal motion, actually, horizontal. Let's say this is a table. Along the table, I am rotating an object in circular, and mass is not affecting me. It's towards the table. Reaction force from the table puts it into equilibrium, and only forces I have along the T direction is Fc. If I have an horizontal circular motion, that is the case. At every point, tangential tension is the same towards the center, and is always equal to Fc. This is an important point. T is equal to Fc at A, B, C, and D. If we, however, have a vertical motion, let me delete that and remind you that as well, and then we are done. Let's say I have the same rope now along horizontal. Instead of horizontal, I have along vertical circular motion. Circular motion, and I'm looking at the same points. Now mass interests me because I am rotating my object now along vertical. Mass will be pulling down and pushing down always, and the tension along the rope, or if this was a car going around the track, the normal force from the surface will be changing. So let's say this is a rope first, and we're looking at the tension at point A, point B, point C, and point D again. At point A, we have tension inward, Fc outward, mg is pulling down, mg will not have effect on it, and the air force, the lifting force from the air will be putting mg in equilibrium. So we're not interested in this part in here. Here at the point A, T is equal to Fc. So at A, point A, we have T is equal to Fc. This is for vertical, if we divide these. So at point B, we have tension pulling down, so we have the rope. We also have mg, the weight of the object, pulling down. And outward here we have Fc. System is in equilibrium. For the safe motion, at least should be in equilibrium. Fc, upward direction forces. So at point B, upward forces are equal to downward forces due to equilibrium. Total force is 0. And in the second law, actually, we will have tension plus mg. So we have T plus mg is equal to Fc. And from here, we can find tension. At point C in here, we will have the same situation as A, and this is always the case. We have tension inward. Let me call these actually TA, will be more definitive, TB, TC, and here we will have TD, always toward the center, the tension. And let me change it as well, TA and TB. Now at point C, we will have TC pulling inward, FC outward. We are not affected by MG again, it's downward. So TC is also equal to FC. Let's put that. And we don't have MG effect in here. At point TD, we have MG down. And now FC, centripetal forces, is the same direction of MG. Downward forces MG plus FC. Upward forces only TD, and they are equal to each other because the system is in equilibrium. So at point D, we have mg plus fc is equal to td, and we can find td from there. If we happen to have a circular motion in a track, like in the roller coasters, we'll be looking at normal force, and don't forget, now we don't have tension, we have normal force. And normal force is always away from the surface. Make sure you show that. So sometimes there could be different surfaces. Make sure that you show always the normal force is away from the surface and perpendicular against the forces acted on the surface. So if this was your surface, let's say circular motion is inside here, for example, this is really interesting and shown in your book. So the car is going inside the surface. So the push on the surface here will be Fc only, right? Mg is down. And normal force will be away from the surface as always. Let me show this. So downward forces at this point, Fn plus mg is equal to Fc. The same thing, now we have only normal force. However, if the car is going on top of the surface, you have to be careful here, that's what makes physics so much fun. If the car is going on the top of the surface, now this is the center of circular motion again, but the car is on the top. For instance, this, we have still mg down, and Fc is always away from the center as always. So let me put Fc as well on the car, we have Fc. But now the surface is this, and the push on the surface from upward, the normal force is, again, away from the surface, will be in this direction. Now what we will have, if the object is moving in this way, we will have total forces upward, Fc plus Fn is equal to mg. Now if also we have a situation where the object is going, it might not feel any Fn, which means if Fn is 0, sometimes it happens, we say what is the minimum velocity to pass this point safely, where the minimum velocity, when we talk about minimum velocity, Fc is equal to mg. This is the minimum velocity, then Fn is 0. It's not disappearing, it's still there. Fn is 0, and in this equation Fc is equal to mg. Now if we have a slightly larger mg than Fc, which is even safer, makes it even safer, then we have a value of Fn. So if a question is asking us what is the minimum velocity that the objects can pass a point safely, we always say mg pulling down is equal to Fc pushing up. Forget about Fn because it will be 0. And if the values are given, they're asking about the Fn or tension in here, then we use the equilibrium. In the minimum case, the system is still in equilibrium, minimum equilibrium, but there's no push on the surface or pull on the tension of the pull on the spring because Fc and mg are equal here. Up position, generally they ask us. And that's how it works. So we'll be solving some questions. Hopefully this was helpful, and see you.